Hi everyone, good morning. First of all, I want to thank all of you for coming to this talk. I know there is a bunch of other very sensible and very good talks around here, and you guys chose to come to the crazy one about using Git as a NoSql DB. And the first question I usually get asked is why? Why would you do that? So my name is Kenneth. I'm a .NET developer. I'm a Microsoft MVP and usually do C#, and I work at a company called AppyParking. So what we do is we digitize the curbside and every parking space there is and all the rules, and put that into an application that you can use on the road to find parking spots. Now, the way we get that information is through taking images about rules, and you have these kinds of crazy rules about where you can park, how long you can park for, what you have to pay when you get towed. And on the other hand, we do LiDAR scanning of the road, so we have the exact dimensions of everything on the road, and what you see there, that image, is not just an image taken, that is an actual laser scan of the road up to 2 centimeters of accuracy. Now we pour all of that into our app engine, which calculates all the rules. Now the thing is, there's a lot of machine learning going on, predictions, and we don't always get it right. So what happens if you have a database with 20, 30, 40, 50 gigs of data and you input data that is incorrect? Well, then you have to go to a backup and you have to restore it, but you have to do that multiple times a day. And we started building something where you could roll back and versioning, and then we thought like, hey, wait a second, Git does all of that. Can't we just use Git as our data source? And the first reaction was like, no, that won't work. But we started thinking about it, and then we did some trials, and effectively we saw that it was possible. So I want to structure this talk into 3 parts. So the first one is, how do we do that? What are the mechanics behind it? Why it is a really fantastic idea and you should all start using it, and then why you probably shouldn't, and what are the disadvantages about it. So first, a couple of disclaimers. When I talk about a database, I'm not necessarily talking about your enterprise scale Oracle or MS SQL or whatever. I'm talking about anything that can hold a bunch of structured data and potentially accessible in different ways. And then NoSql, which is a very overloaded term. I want to talk about NoSql specifically as being schemaless and non-relational, which is the case for Git when we use it as a database. So our first attempt was obviously way too naive. So how would you go about using Git as a database? Well, you can simply initialize a new repository, go into that directory, write a file to the file system, add it, commit it, and then you can get that file back. So you have a key value store. Now the problem here is that for every write I have to do to my database, I first have to write a file to the file system. That's highly efficient, and it also ensures that if you want to create branches, well, you need to have one directory for each branch. So it's not only inefficient in terms of performance, but also in terms of disk space. So let's take a step back and look at what a Git repository is and what's inside it. So if you look on the client, you'll notice that you'll have a .git repo, and then you have your files next to it. That's on the client, and what you have in those folders is essentially a view on your Git repository. So your Git repo has a whole bunch of branches, and they change over time. Now your files is one branch at one particular point in time. But actually all the information is already contained in the .git folder, and if you look on the server, you'll see that you just have that .git folder. So the bit on the right is everything that's inside your .git folder. So everything's already there. You don't need a specific view if you're going to access it programmatically, rather than working with the files directly. And the Git Data Model, we all know about branches. And a branch essentially references a commit, and that one references the previous one and the previous one and so on. And so that's how we build up a history of our code, or data in this case. And we point a branch at one of those commits. This is kind of the model that we as programmers are familiar with and we use on a day-to-day basis. Now, one level below that, we have trees, and you can look at a tree as a folder. So every commit points at a certain folder, or a tree in the Git terminology. And those trees then reference blobs, which we can think of as files, or other folders. And what's kind of particular about Git is that there's two databases, in fact. We have everything on top, which is the reference database, and that includes branches and tags and things like that. And we have the object database. And the difference between those two databases is that the top one, the reference database, is a read-write database. You can move your master forward, backwards, you can create new ones, you can delete old ones. But the object database is in fact append only. Once you write a blob to it, it's never gonna get removed from there. You also can't change a blob. If you want to change a blob, what you actually do is you create a new one. And because of that property, we can look at the history, because we know that nothing will ever change what's already been written. And Git gives us a bunch of commands to work with this. We have the parseling commands, and whether you've been working with Git on the command line or through tools, a lot of these will probably be very familiar. Merging, pushing, doing a git log, a diff. So these are like the high level commands. And underneath that, we then have the plumbing commands. Most of those will probably not be familiar, because what Git does is, with the parseling commands, it constructs these from the plumbing commands. And as I found out, if we want to use Git as a NoSql DB, we're going to get our hands dirty, and we need to dive into the plumbing to access the Git database directly rather than through the file system. So let's start by accessing the Git database directly. So the first thing we need to do is we want to use Git as a key value store. So we want to put in some content and get back a key, and then with that key we want to obtain that value again. So the first thing is to write a blob, and we're going to do a simple echo of a piece of JSON string, and then hash that object and put it into the Git database. And that gives you back a hash. So you got a long hash and a short hash. And the specific property here is that the hash is completely dependent on what's in your file. So if I execute this command on this PC or a different PC in a different time zone, different area, it's always going to give me back the same hash. Now with that hash, I can then read the file and get it back. So we have a key value store. It's a bit of a lousy key value store though, because if I change my content, my key is gonna change. So that's not very helpful. So let's give that file then a name and put it inside a folder. So I want to write now a tree, and you have the very helpful command update index, which is counterintuitive, but what you're saying is I want to stage a change which says that this commit hash is now called 1.json. And then once you have those changes, you're going to tell Git to write it to a tree. And that again gives you back a hash of that tree. So I can now read that tree, and it'll tell me that this hash is now named 1.json and it sits inside that tree. But still, I need to know the tree where it's in, so I need to step one level up and go to the commits. I can update a commit message and say like, this is the tree I want you to reference. It will then give me back again a hash, and I'll have a commit that points to a tree which holds a reference to my blob that I had. And now I can do a log, and you get the output that you would normally expect when you're working in code. And now, referencing the commit hash, I can go directly to the name of my file, and it will give me back my output. Now I want to update the blob. Suppose my JSON value has changed, but as I mentioned before, you can't update that blob directly because it's read-only. So what I'm actually doing is I'm going to write a new one, and now when I write the tree, I'm just gonna give it the exact same name, 1.json. Again, I'll write a commit, and now I can do a log, and I can see that at first I had a file, and then it was changed in a later commit. So you can see that the second commit I wrote has a reference to my older one, and that's why Git knows that, you know, this was 1.json in that commit and this was 1.json in the other commit. And I can show the file content of 1.json in the new one and in the old one as well. So now I have my two versions of my files, both being able to reference through the commit. Now I'd still need to know which commit is the latest one, and for that we can use branches or refs. And I can just tell Git the reference named master now points to this commit, and now I can access my file by going show me whatever is the value of 1.json on master. So that's all nice, but this is all shell commands. I'm a programmer. How do I do this? Do I, in my program or in my application, do I always go to the shell and back? We tried that and it didn't work. So how can I access this now from code? So there is a library called libgit2, and what this is Git but implemented through C. So we can use that to programmatically access Git. Now the problem is I don't know any C, so the next step was finding something that I can use, which is libgit to sharp. So I'm a C# developer, and that provides bindings over libgit2, so I can access it from C# code. And there's bindings for Java, for Node, and Python, I think, as well, and a bunch of other things. So you can access that through any language that you want. So let's now start and build a Git database in C#. So first of all, what do we want from it? It's a key value store, so it's usually a save method with a key and a value, and then a get method where I pass in the key and I get the value back. With Git, we add one more thing though, and that's the branch. So we have two methods, getting and saving, where I pass in the branch, key, and a value. So the first thing I need to do is initialize a repository, and you do that with this kind of piece. So different bindings will have different methods of doing that, but the important thing is that we want to initialize a bare repository. So we don't want the files on the disk, we want it directly inside the Git database. So let's do now the same exercise as we did before through the shell, but through code. So the first thing I'm going to do is create a byte stream of the value. Like I pass in an object and I just want a stream. Now I tell Git to create a blob. It returns me the blob which has the hash and everything. Then I write a a tree, but when I write a tree, I need to copy the previous one, because otherwise I'm going to lose all the values that were in there. So I get the current commit and then copy that tree from the tree it's pointing at. I then add the blob to it and then write it. So it's now created a tree which is pointing to a blob. And now I commit that one, and this is kind of familiar. You have the create commit command where you pass in the author and the message, the tree it's pointing to, and then the parents. So the parents here is a list of commit. In this case we just have one commit because we just referenced the previous one. You could have multiple ones in cases where you do merging, where you have multiple parents. So I write a commit, and then lastly I need to move my branch pointer to the new one. So I get that reference, and then I update the target to point to that one. And lastly I'll return the hash. So now I've written a file to Git, so how can I get it back out? Well, to get it back out, we'll have to do the reverse operation. So we started by writing a blob, a tree, a commit, and a branch. So now I'm going to start from the branch. Then I'll get the tip of that branch, which is the commit. I'll get the tree, and then I'll get the blob. I can get the content of that blob and then just deserialize it and turn back the object. So now I've got in C# a basic key value store where I can get my values based on a branch and a key, and I can write into it. So that's all nice, but you know, I don't want to do this every time I write code. So what we did at Happy Parking is we created a repo that does all of this, because this is kind of like the essentials of it, but there are a couple of things that you need to take into account when you do all of this, which I'll talk about in a moment. But we open source this, so if anyone wants to use it, they can just grab it from GitHub and do that. So we're working on a .NET Core version, which means that it will also be available on Linux, on Mac, on Windows, wherever you want to use it. And we also created an HTTP layer on top of it so that you can have a Git repository somewhere else and have multiple applications from multiple locations access it directly. So you can grab that, or if you're just interested in looking at the code, just go to that URL and everything is there. So I want to switch it up now a bit. So this was the how. So that works, we've tested that. And I want to talk a bit about why you would do that and what are the advantages. And there's advantages that are specific to Git, and there's advantages that are specific to a NoSql database. So the first one is not really Git related, it's schemaless. And schemaless doesn't mean that your application is schemaless. You know, your application is gonna expect some kind of format. Schemaless means that your data store doesn't care about it. Like Git doesn't care what kind of content you put in your JSON files. If today you have an ID and a name, and tomorrow you add a bunch of other properties, Git is not going to complain about it. It's not like a SQL database where if all of a sudden you add a couple more columns, well, you need to tell the data store about it beforehand. Git doesn't do that, so it allows you to add properties. The next one is Git specific though, versioning and rollback. So if you've used SQL or Oracle or another database, I'm sure you'll come across the typical updated column, the deleted, which is 0 or 1, and then the update date. And then you look at the update date and you say like, right, this was updated last week, but you don't have the previous value. So essentially, you know someone screwed up, but you don't know what. And Git gives you the possibility to look into history and see everything that has changed over the course of your application. So it's fairly simple. I can show the current value, then I can move master, and then I have my old value. So I can roll back the entire thing, or if I want, I could just look at the previous commit. I don't actually have to update the state of my data. I can still leave master where it is, but look at what was there before. Then there's diffing. You want to know what has changed over time. So in this case, I can just do a diff between the content of one.json between these two different commits, and I see like, right, something is wrong with this data, but what has actually changed? So by doing a diff, I can get the previous and the current value. And if you, in this instance, I've written the JSON on one line. If you would have like a JSON which is formatted, then you'll get the exact lines where it changed, so you can see the exact properties that changed over time. And you can do things like git bisect, where you take like a large range of commits and then you go looking for where that particular piece of data has changed. Backup and replication then. So this is not only for Git, like SQL, Oracle, any NoSql DB has backup built in. But if you've ever configured backup for SQL, for example, then you'll have done monthly backups, weekly backups, different retention policies. The thing is with Git, that's not necessary because you already have the possibility to go back at any point in time. And it's actually very simple to do a backup of Git. So you could copy the folder, which is one way of doing it, but you could do a much faster backup, and it's by simply creating a remote and pushing your changes to that remote. So at that moment in time, you create a copy of your repo on GitHub or whatever other source you have, and you just push all the changes there. And that way, you only push whatever has changed. So your backup is a lot faster, and it's about 2 lines of code to do that. Then replication. Replication is essentially just continuous backups. So what you can do in Git is you can create a hook, which is a piece of script that gets executed after every commit. And you tell it that after every commit, do a push. So that means that if I save a value, it's immediately pushed to a separate repository. And I could create multiple remotes, so I could create 10 repos distributed all over the world and push to those remotes continuously. And that means that my data is completely replicated with just 3 lines of code. So backup and replication is very powerful with Git, and it's very easy to configure. Transactions. Obviously you want to have transactions in your database. Normal databases have transactions. Git has 2 types of transactions. So the first one is a short-lived one. So if you want to do a quick transaction of a couple of files, you can just write a whole bunch of blobs to the file system, and as long as you don't do anything else, then it's not part of the data. So even though there is a time between them, and then I can add all of them to a trees, I'll get that tree back, and at this moment I decide to either commit the transaction or just don't do anything, and then my transaction is not applied to my data. So in this case I'm doing the commit, and then all my files get added in one go to the database. So the commit is is transactional. It's either all committed or nothing is committed. And those are short-lived transactions, the same as what we know from relational databases. But Git has actually another type of, an interesting type of transactions, and that's long-lived transactions. So what happens if you need to do some work on an application, and you get some files on Monday, then you get the rest on Wednesday, and the last bit on Friday. So what typically happens is that you wait until you have all of them, and then you start inputting them. With Git, what you can actually do is you can create on Monday a branch, you add some files to it, and you just leave the branch there. Then on Wednesday you get some more, you add some more, and on Friday you actually say, right, I'm gonna go back to master and I'm gonna merge in this whole thing. And at that point, either everything is applied or nothing, which is again a transaction. And that allows you to keep work in progress to be separate from your main data or your live data. And then we have tooling. So if your app is using GitDB, Git as a database, underneath it's still just a Git repository, which means that you can use any Git tool that's out there to access it. So you could use Git bash to interrogate your data, to navigate through it, to do all the diffs, bisect, whatever you want. You can point a Bitbucket server to it, do pull requests, do diffs between branches, or source tree to check on it locally. And that all works with your Git repository. So the tooling is there and you can reuse it. You don't have to write all of those interface tools. So those are all reasons why it's a good idea to use Git as a DB. I want to talk a bit about the problems that we saw and that we encountered while using it and what we did to solve them. So the first thing is also not a Git specific problem, that's queries, but it's a problem that happens with all key value stores. So how can you query it? Well, you need to know the key. You need to know your exact file name and the path that leads to that file name. You can also query by prefix, sort of, which means that if you know the folder, then you can get all the files in that folder. So it's not recursive, it doesn't go all the way down the tree, but you can get a list of files by just getting the folder name. So how do we solve that? Well, just by avoiding the problem essentially. If we can't read from Git, then let's just write to it and read somewhere else. So what we did is we implemented a CQRS system on top of this. So all our writes go to Git and all our reads are coming from Elasticsearch in our case. But it could be SQL, it could be any other NoSql DB. And that's a common pattern, CQRS. But with Git you actually have one advantage, and that is that you have commit hooks. So whenever a commit occurs, we actually kick off a script that does the diff and then indexes those changes. This does mean that you have eventual consistency, and it has all the advantages and disadvantages that eventual consistency brings with it, so you have to take that into account if you implement a solution like this. Then there's the question of concurrency, and concurrency can happen at various levels. So the first one is when you're creating blobs. So what happens if I write the same blob twice? Well, actually, as I explained before, your blob is based on the content of it. So even if I write twice the same blob, that's fine. There's no problem there. So we don't have to worry about that one. The next one is when we're writing trees. And with trees, we could have an issue. So suppose the case that a client comes in and says like, right, I want to add a new blob, so I'll copy the tree and write a new blob. Now before I can update the commit, another client comes in and says, I also want to write a blob. So it comes in, copies the tree A, because that's the active one at the moment, and I'll write that blob. So now you have an issue because the second blob is now not contained within that new tree. And a similar thing occurs one level up when we're doing the commits. So First client comes in, creates a new commit that references the current active one. But before I can move the branch, someone else also creates a commit referencing that same commit. And then when I move the branch, I'll lose access to my other commit. So you can't have concurrent access at that level. So the way we solve that is by not allowing concurrency within a branch, because as long as you're writing on two different branches, then there's actually no problem. Then another one is performance. So we actually did a bunch of benchmarks on it, and we got to 125 writes per second. Now that's not great if you compare it to SQL or Oracle or whatever, or MongoDB, Elasticsearch. But on the other hand, I would say, and this is a completely made up number, but about 80% of the applications don't need more than that. If you have a CMS or a wiki, it's unlikely that you're gonna have more than even 1 write per second. One thing to mention though is that 125 is for when I have 10,000 files in my repository. Now what happens if you have 1 million files, which is not even that big of a number? You could think of 1 billion files. And when we scaled it up to like 1 million files in our repository, then we got to 18. Now that starts to worry me a bit more, because it's easily possible that it grows to 10 million, 100 million, and then we're gonna have some problems with writing. So to find out the solution for that, the first thing is to look at why does my write speed go down when my files go up. And if you look at a repository, you can see you have your master, your commit, your tree, and then in this case I have in my tree 1 million files. Now what happens when I want to add a blob to it? So my tree is essentially a file, an index file with 1 million lines. Now if I want to add a blob to it, I need to copy that file and add 1 line to it, because I can't update an existing tree. So if I add a file, I create a new tree, I copy the 1 million lines and add 1 to it. So you can see that the bigger my repository gets, the bigger that file is going to get and the longer it's going to take to write it. So that's the cause of our write speed going down while the files go up. So what can you do about that? Well, let's not have a tree that's 1 million files then. Let's nest our trees. So in this case we have folders with subfolders, and we have on the top one tree that contains 100 subfolders. Each one of those subfolders has 100 other ones and 100. So 100 blobs in each of the last level ones. So I still have 1 million files, it's just that they're structured differently. So now what happens when I add a file? In this case, I need to update the tree on top of that, which is just 100 lines of index, and also the one on top of that and the one on top of that. So now I still have a repository of 1 million files, but when I add something, I just need to update 3 files that are 100 lines rather than one with 1 million. And you can expand this, you can make 4 levels or 5 levels or 6, but about 3 or 4 we found was kind of like the golden point for not having to modify a lot of files. And when we did that with our repository of 1 million lines, we found out that we had doubled our speed in comparison with the 10,000 lines that we had in the beginning. So 250 writes per second, and that's actually a decent amount, a decent speed, and it was more than sufficient for what we needed. Now you can go further and you can look at more solutions. So if one repository gives you 250 writes per second, well then, multiple repositories give you a multiple of that. And that is good if you can partition your data. So it could be different countries, different customers, where you can have a repository for each one of those. And then another solution is if your disk is the major pain point or the bottleneck, there is a possibility in libgit 2 to replace your disk with a different backend. So we write it now to disk, but you can swap it out for a Redis, a RavenDB, Elastic, Memcached. And I did try this, and funnily enough, it got slower. And the reason it got slower is because I was using a single node. So if you do have a single node, then you have the overhead of doing it over HTTP and then still writing it to disk. But if you have like a very big repository, then you can do sharding over multiple servers, and you can actually have a distributed Git, which is 2 levels deep, but that would be a lot faster as well. And then the last issue is merge conflicts. So I'm sure that all of your merges go like this, but if you're working with data, this can also happen. And what is the solution there? Well, there is no real solution, because this is not so much of a data store problem. This is an application level problem. If I update something and my colleague updates that same thing, the data store cannot automatically know which one is the right one. So one possible solution that you could have is, if we have a merge conflict, just store it. Store the 2 versions side by side, and the next time you read it, ask the user like, hey, we found this, which one is the correct one? Or you could use the existing merge tools, or you could build your own merge tools on top of that. So we work with geospatial data. What we did is, if you put in 2 shapes, we just save them, and then we have periodically someone who reviews like 2 shapes on a map and then selects the one which is correct, and then we save the merged version in there. So to summarize, one, do I think it's a good idea to use Git as a DB? It's when you have content heavy applications such as a CMS or a wiki, where you're gonna have at most 1 write per second, or maybe 2 if you're lucky and 2 people press the same button. Or if your data is partitionable, you can do it over multiple countries, multiple customers, and you can create different databases. One is not such a good idea if you need fast writes. Don't write a trading application with GitDB, because it's gonna blow up. Or if you need immediate consistency, so when you have when you need to replicate all of those changes to a read optimized store, there's gonna be some delay. So sometimes you may have to rely on eventual consistency to get things right. If you don't need it though, then this can work. So one other application that I've seen of using GitDB is someone had a project doing in areas where there was no internet connection. So what they did was they took GitDB on a USB stick, plugged it into computers, got all the data in there, and then multiple people were doing that in different locations. And then at the end, they just bring everything back, push everything to one remote, and then merge the data at that point. So that can be really handy if your data has to be disconnected at some point and you do have to merge all of it together. I don't have time for a demo, but I do have all the code online, so you can check that out. And I've also written a blog post which reiterates all of these things and a couple more. And the only thing I would like to leave you with is to use and abuse your tools. They are there to serve you. So I hope you enjoyed the talk, and thank you for your attention.